morning everyone. So, we will start with the macroscopic balances in fluid mechanics, and I think you have already done some of it, right? How to do the macroscopic balance, how to select a control volume in a flow regime, and how to apply the equation of continuity, that is mass conservation, equation of motion, and energy balance equation. Energy balance equation you already know, because it is basically Bernoulli's equation, total energy in equal to total energy out under a steady state condition. And during the discussion of boundary layer, I think Professor Dasgupta has already given you some introduction in the macroscopic balances, isn't it? So, anyway, we will refresh some of the concepts and definitions, and then we will go to the problems directly. Now, for a control volume, first of all you have to select a control volume of your system. Okay. Suppose you have a flow situation something like this. Suppose there is a nozzle, and it is a pipe. Water is coming in with a velocity v1. The cross sectional area is, let us say, a1. It is going out with a velocity v2 and a2, and whole this thing must be kept over a support. Right. So, suppose this flow rate is known. Flow rate is known means a velocity is known, knowing the cross sectional area. So, doing an overall material balance, you can find out the velocity at the outlet. Now, because of the liquid flow, the control volume will be exerting some kind of reaction force on the supports in the x direction. Okay. So, so there must be some force should be there, which will be kept this whole assembly in place. That can be obtained by doing an overall momentum balance. Okay. And similarly, you can do other calculations by conducting an energy balance equation. So, you have to select a control volume for a control volume, that is important. The generic equation of any property is written in this form. It is like the material derivative that we have discussed in the course TPA transport process 1. N is any property, any arbitrary extensive property. It may be mass, it may be momentum. Okay. So, this is kind of total derivative or material derivative. This is kind of your local derivative, and this is basically the convection terms. Okay. And rho times v dot dA over the control volume is basically giving you the mass flow rate, and this is a vector multiplication. So, this is a scalar product, and this v dot dA will be assuming a direction. It will depend. Suppose this is the control volume, this is the inlet A1 you are talking about, and what is the direction of the area? Outward normal. Direction of the area is outward normal, and suppose V is in this direction, then this product will be assuming a minus sign. If both these are in the same direction, let us say at the outlet, they will be positive. If this is inclined with an angle theta, then you will be taking the horizontal projection of normal, outward normal in the x direction, if you would like to do a momentum balance in the x direction. Similarly, you have to take the other component whenever you are doing a balance in the y direction. This gives the time rate of change of the property within control volume. Okay. And what is eta? Eta is basically intensive property, that is the property we are dealing with divided per unit mass. If capital N is mass, then eta will be 1. If capital N is momentum, then eta will be V. So, therefore, rho dV will be mass content in the control volume. Okay. This is known as efflux of net rate of flux of the property across the control surface. So, this is basically the mass, differential mass within the control surface multiplied by velocity. If capital N is a momentum, so this will give you the momentum. This is mass, this is velocity, so it will be giving you in effect total momentum. So, conservation of mass or equation of continuity in the integral form, the differential form of the conservation equation of continuity is del u del x plus del rho del t plus rho del u del x plus del v del y plus del w del z is equal to 0, and this is basically the integral form of conservation equations. Okay. Now, at the steady state, this time derivative will be off. So, you will be having integral of Cs rho control surface rho v dot dA. Okay. I think all of you have, I think these are already been done previously to some extent. Now, the momentum equation becomes now the control volume can be of 3 types. Control volume is fixed, okay, like the nozzle we are discussing initially. The control volume is moving with a constant velocity. Okay. A control volume is accelerating. If the control volume is accelerating, then it is called a non-inertial frame of reference. If it is stationary or moving with a constant velocity, then it is inertial frame of reference. Okay. But if it is moving with some kind of uniform velocity, all these velocities or the quantities we will be discussing, those will be with respect to the control volume, that is the frame of reference that is fixed to the control volume, and you are measuring the velocity from a fixed, let us say from the ground. Okay. So, all the velocities will be the relative velocity. Now, the first one will be considering a stationary control volume. Our stationary frame of reference is capital X, Y, Z, that is, let us say, fixed in the ground. Okay. and control volume is all the quantities with the coordinate system x, y, z that is attached with the control volume. Okay. So, in the first case, when the control volume is stationary, then small x, y, z and capital X, y, z they will be identical, there will be absolutely no difference. When the control volume is moving with a uniform velocity, then we will be writing all our quantities with respect to x, y, z coordinates, because our control volume is fixed with the moving system. So, all the velocity, and you are measuring velocity from the ground, that is with respect to x, y, z. So, it will be all the velocity quantities will be replaced by the relative velocity, and the non-inertial frame of reference that we will discuss is later on. So, first we will discuss about the fixed control volume. Let us say the property n is momentum. So, eta will be velocity. Okay. So, the form of momentum balance equation will be like this. Now, this is dp dt is rate of change of momentum. So, it is by Newton's second law, it is basically the sum of the external forces. Now, these external forces of two types, one will be the surface forces and there will be the body force. Okay. The surface forces will be viscous forces, okay, and pressure forces, and body force will be gravity. If you apply any external electric field throughout the whole volume, then it will be the external electric field, so on and so forth. So, basically if you neglect the viscous forces, the surface force will be nothing but the pressure forces. And body force will be acting throughout the whole body of the control volume, throughout the whole volume of the system. So, if it is per unit mass, then b multiplied by rho dV will be give you the total body force of, so this integral will be the over the volume, and this integral will be over the area, because it will be acting on the area, this pressure force, and the body force will be acting throughout the whole body of the material. So, it will be over the volume. So, you can write down three equation of motion, force balance in x direction, y direction and z direction. In general, so this will be del T of C V u rho d v. U is the velocity component in the x direction. Okay. F s y plus f b y del T v rho d v plus v rho v dot d a. This whole quantity will be basically the mass dm in the control. So, mass times velocity in that particular, the velocity component in that direction will be give you the momentum in that direction. Okay. Is W rho V dot d a. So, these three will be the momentum balance, three momentum balance equation in three directions. Okay. Now, let us, so this is quite simple. Next, we look into the control volume moving with a constant velocity. Okay. So, all the velocity components can be replaced by velocity components, the relative velocity components. Relative means your coordinates. Suppose a jet is a water jet is falling on a vane. Okay, it is falling on a vane, and it is moving up and coming out in this direction, and this vane is moving with a constant velocity in the positive x direction, let us say at constant speed 5 meter per second. So, what we will be doing, we will be fixing our control volume along the vane, maybe something like this, and doing all the balances. Since our frame of reference is fixed here, and all these quantities will be with respect to this frame of reference, but they will be measured only if you are standing outside on a fixed frame of reference. Okay. So, all the velocity components will be basically relative velocity compared to the frame of reference, stationary frame of reference. So, your force balance equations become Fs plus Fb is equal to del del T V x y z rho dV plus control surface V x y z rho V x y z dA. Now, V x y z is nothing but the relative velocity vector. Okay. You can break down this equation, vector equation, in the three directions f x, f y and f z. Only this V x y z will be the relative velocity component in the x direction, relative velocity component in the y direction, relative velocity component in the z direction will be replaced. Okay. So, I will be just writing one or two equations. Okay. So, this will be basically the x component. Equation of motion or momentum balance. Similarly, you can write down the y component and z component. Okay. Anyway, with this background, we will start solving the problems. Basically, whatever I have done, I will be taking up the problems, those are appearing in the there are so many problems on these topics in the exercise of Fox and McDonald. Okay. I will be just arbitrarily taking some problems. In fact, what I did, I started solving all the problems in the exercise, but there are so many problems, more than 100 problems are there probably. So, in fact, I have reached up to 50. So, but it is not possible to solve all the problems in the class. So, what I will do, I will just pick up some typical problems even from the examples, because they are very good problems to demonstrate how the concepts. Okay. I will take up one or two problems from the examples, and rest I will take all the exercise problems. Okay. Whatever I feel that those are necessary for giving you new concepts of doing things, and then you should try attempt the problems, give other problems given in the exercise, and if there is any problem, then we can sit down and solve it out. Okay. The first problem is an example problem. You have a multi-port system, multi-port device. In a multi-port device, there are number of ports of inlet, number of ports of the outlet. Suppose you have something like this. This is phase 1, this is phase 2, phase 3, phase 4, this angle is 60 degree, and this angle with horizontal is 30 degree. Okay. And fluid is coming in across the phase 1, it is coming in through phase 4, okay. It is going out from phase 3 and it is going out from phase 2. Now, it is a steady flow, and your A1, A2 etc. all specified 0.02 meter square, A2 is 0.05 meter square, A3, A4 is they are same 0.04 meter square. The mass flow rate in section 3, that is given as 56.7 kg per second. Volumetric flow rate across the phase of 4, that is given 0.03 meter cube per second. V1 is known, it is 3I, okay, meter per second, and properties are uniform, means density will be appearing, you are considering water as incompressible. So, density will not change. So, question is what is V2. So, you have to select a control volume something like this. This will be normal to this, so that in fact does not matter, you will be doing a material balance. So, you will not be taking any component. So, just take a control volume around this device and apply the overall apply the conservation of mass at the steady state. The transient part will be off. Okay. Now, the direction of this becomes important, the sign of this. So, you will be having control surface where the fluid is intersecting the control surface, that is surface number 1, phase 1, phase 2, phase 3, phase 4. Okay. So, in fact, this product V dot dA will be negative for this phase 1, because area will be having a direction in the opposite and opposite to the velocity. Similarly, for phase 4, velocity is coming in and area will be the normal away from it, and for 3 and 2 they will be in the same direction. So, V dot dA will be having positive sign. So, it becomes V1 A1 plus V2 A2 plus V3 A3 minus V4 A4. Okay. So, V2 A2 will be V1 A1 minus V3 A3 plus V4 A4, and your V2 will be V1 A1 by A2 minus V3 A3 by A2 plus V4 4 by A2. Okay. Now, the various quantities are known. You know V1, that is 3 meter per second, V1 is known. You know Q4 dot, that is the volumetric flow rate. So, this will be nothing but V4 A4, right. This is volumetric flow rate, velocity times area. So, since area A4 is given, you can find out V4, it comes out to be okay, you can directly substitute. Okay. So, M3 dot is nothing but rho V3 A3. Okay. So, this is 56.7, and you can find out V3 A3 taking rho as 1000 kg per meter cube for water. So, it comes out to be 56.7 into 10 to the minus 3, and can substitute the values, and it comes out to be 0.666 meter per second. And of course, since it is in the downward direction, in the vector notation V2 will be minus 0.67 J meter per second. Okay. So, in this problem, what will be striking or that the angles given in this slanted port and this slanted port and this slanted port does not you never utilize them. You are doing overall material balance. Now, if you do momentum balance, whenever you will be taking the components, then this angle will be come into picture and they will play some role. Okay. This is an exercise problem 4.25 from Fox and McDonald. This says that there is a tube and water is moving into the tube of height 2h, the full height 2h and width in this direction perpendicular to the plane of the paper will be let us say w, and water entering with a uniform velocity u0. Okay. And whenever it is moving out at the exit, this phase number 1, this phase number 2, at the exit plane the velocity will be having a parabolic velocity profile. Okay. And it is given by some parabolic equation. So, at 1 velocity is v1 is basically nothing but u0, that is uniform velocity of plug flow. At 2 you will be having velocity v2 by u max is a 1 minus y square by h square. Okay. And your y is measured from the central line. That means, your coordinate system is fixed at the central line. This is x, this is y. Now, the question is find out value of u max in terms of h and u0. Now, what you have to do? You have to select a control volume, let us say a rectangular control volume within this a cylindrical control volume, no sorry it is a plate. So, a rectangular control volume between inlet and exit, and apply the since it is a steady state, conservation of mass, material balance. So, rho v dot dA should be equal to 0. Now, it is incompressible. So, rho will be off. Now, the phase 1 v and dA will be in the opposite direction. So, this scalar product will be negative and velocity at phase number 1 will be u0 minus u0 into a will be nothing but 2h times w, right. That is the normal area, the flow area normal to the flow area normal to the flow. Okay. Plus now v dot dA. Now, at the exit point this velocity will be varying with respect to y and dA will be nothing but w times dy, right. So, you have to really carry out an integration here. Now, since y is measured from the central line, so it will be double twice, because by doing this integral v2 will be which will be a function of y w dy. By carrying out this integration, you are doing the total material that is coming out of this half. If you do an integration from y equal to 0 to h, right. So, it will be twice, because y is measured from the central line because of the coordinate system. If y would have been measured from the bottom, then this integral would have been v2 y w dy, then 0 to 2h. Now, this w will be go and this will be equal to 0 at the steady state, this will go off. So, u0 and this 2 will be also off, u0 h is equal to 0 to h, v2 will be nothing but u max 1 minus y square by h square dy. So, this will be h minus h cube h by 3, right. So, 3h 2h by 3. 2h by 3 . 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 2 this H will be off. So, you will be having basically u 0 is equal to 2 by 3 u max, okay, and u max will be 1.5 u 0. So, if u 0 is given, you can find out what is u max. Then again problem number 27. In fact, what I was thinking that in the exam I should have told you, because it is open book, I should have given you numbers. Do the problem number 4.30 or something like that. Need not to copy these problems. They have very good collection of problems. You have a 90-degree bend. Now, if you have a solution manual of that Fox and Maclo, then it will be problematic. I do not know whether it is available or not. I do not know. So, phase number 1, this is phase number 2, this is a 90-degree bend. It is a square channel. Width h, this is h. Achha. Entering velocity, entrance velocity at 1 will be the uniform velocity, uniform, that means V 1 equal to u. Okay. Now, the channel makes a 90-degree bend and it distorts the flow to produce a linear velocity profile at the exit. Now, the velocity profile at the exit is linear, it is not uniform. Because of this 90-degree bend, the velocity profile is distorted, and velocity profile at point number 2 is a linear velocity profile, something like this. V max, V min, okay. It is a linear velocity profile. That means at x equal to 0, here the velocity will be maximum, some V max value, and at x equal to h it will be a V minimum, and it is a linear fall. Okay. V max is given as twice of V minimum. U is given as 7.5 meter per second, that is a velocity, uniform velocity at entry point. You have to find out V minimum. What is V minimum? Okay. So, again you have to select a control volume within this flow area, and this operation is under steady state, and you have to do an overall material balance. Okay. Now, at point number 1, your it will be u times h times w, that will be the total material in at point number 1, and point number 2 this will be w. Since velocity is varying with this h in the x direction, so again it will be, since it is given a profile, again you have to do an integration. Zero to h, and V 2 will be, since we know it is a linear profile between V max and V minimum, just fit a line like a plus b x, and at x equal to 0 your V 2 will be V max, and at x equal to h your V 2 will be V minimum, and the profile you will be getting will be V 2 equal to V minimum 2 minus x by h. simply because V max is given as twice V minimum. This is given in the problem. Okay. So, then you insert this velocity profile into this integral and carry out this integration. If you do that, you will be getting 0 to h V min 2 minus x by h dx. Okay. So, this will be V minimum 2h minus h by 2 or 3h by 2 V minimum. So, V minimum will be nothing but 2 by 3 u. Since u is given as 7.5, so V minimum will be 5 meter per second. Okay. So, similarly, there is one more problem in the exercise that he has given some other type of cosine profile in the exit. So, it will be the same thing, whatever the profile you have to integrate across the thickness, and the approach remains the same. Twenty-ninth problem in the exercise, it says you have a chamber something like this. The straight part. Now, a section of pipe carrying water contains an expansion chamber. This is basically the expansion chamber. Now, this end is free. Okay. Now, it has a free surface, water comes in, goes out, section 1, section 2. This is section 3, which is free surface. Okay. So, this is basically a shock absorbing section sort of thing, but there is no water going out or coming in through section 3. Okay. It is only a free surface. A3 is given as 2 meter square, A1 is equal to A2 equal to 1 meter square. Now, at a given instant, V1 is equal to 3 meter per second, Q2 dot, that is the volumetric flow rate, is 4 meter cube per second. Okay. You have to find out the rate of change of free surface level at that instant. That means, if this height is h, you have to find out what is the value of dh dt, and whether dh dt is positive or negative. That means, if it is positive, this surface, this level will be rising. If it is negative, it will be receding, falling. Okay. So, it is basically a transient problem. So, you have to write down the conservation of material balance equation and keeping the transient term as well. It is incompressible, so rho will be cancelled out. Okay. Now, let us find out what is dV. What is dV? dV will be the, suppose then you have to take a control volume, let us say something like this. Okay. What is the total volume? I am talking about, I am trying to simplify this term. Okay. The total volume will be volume here, h times A3 plus, but you cannot quantify the volume in terms of area, etc. because this section is bend, there is a bend here, there is a bend there, you can say this total volume is, let us say, some V, which remains constant, but this volume will be variable because H is varying with time. So, dV will be A3H, H is the height at any instant, plus rho V. This is constant, not rho V, is constant volume of the chamber, and this is the portion of the free surface that volume will be keeping up and down. What is that? No, right. There is integral dV, fine, that is fine, total volume. So, it will be basically ddt of A3H plus V will be minus V1 A1 plus V2 A2. This is total mass in, total mass out. Okay. The in one is negative because the area normal vector and the area vector and the velocity vector will be in the opposite direction. So, you will be getting A3 dH dt will be V1 A1 minus V2 A2, and if you put all the numbers, it comes out dH dt turns out to be this is basically nothing but V1 A1 by A3 minus V2 A2 by A3, and it turns out to be minus 0.5 meter per second. Okay. So, that means at that particular instant where this velocity, flow rate, etc., specified, at that instant the the level of the free surface will be falling down. Falls at that instant. In the next instant, your velocity, etc., can be changed and this value can be changed. Okay. Then exercise problem 34. You have a cylindrical chamber, okay, and the water is filled up to let us say diameter d, and water is filled up to this height h, capital H. Okay. Your coordinate system is fixed here. This is y is measured from the bottom, this is x, and you have a small outlet of diameter, cylindrical outlet of diameter d, and liquid will be draining out with a velocity V2. Okay. And it is given V2 is roughly approximated as 2 g y at any instant of time, where y is the level of the liquid in the tank at that instant. Okay. So, basically as time goes on, this level will be dropping, and suppose there is y at any instant, and velocity is roughly proportional to under root 2 g y, is given by under root 2 g y. Now, you have to find out where y is the distance measured from the bottom, y is the height at any instant measured from the bottom. Now, we have to find out the time required to drain off the tank. Okay. Now, at any point of time, the height is let us say y, and we take a control volume around that, and this is the port number 1, or say let us say port number section 2, where you will be the water will be coming out with velocity V2, and nothing is going in, coming in. Okay. So, only one stream is coming out. So, del T rho dV plus control surface rho V dA will be equal to 0, and this will be ddt of 0 to y. Rho will be cancelled out because it is incompressible. dv at times dy, that is a differential volume, and it will be integrated over y. At is pi d square by 4, d is the capital D, that is the area of the tank, plus V2A2. Velocity and area normal both are in the same direction, and there is no entry point. So, this will be a governing equation. At is constant, so it will be At dy dt. This will be At dy dt plus V2A2 is equal to 0. Now, if it is a conical section, then At will be a function of y. Okay, so then you cannot take it out of the integral, then again it has to be inside. Anyway, so dy dt will be nothing but minus A2 by At under root 2 gy. Okay. Now, it is a simple integration. Zero to t, at time t equal to 0, the height was h, at time t equal to t, the height was y. So, this will be root over y, the solution will be root over y is equal to root over h minus A2 by At under root g by 2 t. There is the height at any instant of time. Now, the time required when to evacuate the tank, when this y will be equal to 0, right. Right, and this t will be d square by d square under root 2h over g. Okay. The next one is a momentum balance problem. You have a class after this. Okay, fine. So, anyway, thank you very much. So, we will be continuing doing problems in tomorrow's class, and probably in 2 more classes in the next week. Okay.